In lesson 2.13, we're going to be looking at implicit differentiation. In this section, we'll be finding derivatives of implicitly defined functions. So far, we have dealt exclusively with functions that were explicitly defined. What that means is they have been solved for y. Y has been isolated on one side of the equal sign. But imagine having a function with x's and y's, powers of x's and y's, maybe even x's times y. And it would be onerous to solve such a function for y, but imagine that even if you were successful at that, you were then tasked with calculating the derivative of that function once it's in that form. Fortunately for us, we don't have to do that. There's a much easier way, and that is implicit differentiation. So the first thing that we have to do is to realize that we're going to be differentiating with respect to x. And this is something I'm going to be talking about as we go through this. When you differentiate terms involving x alone, you can differentiate as usual. But there's also a notation for differentiating x that may remind you of this, and I'll model that for you in a little bit. When you differentiate terms involving y, you must apply the chain rule because you're assuming that y is defined implicitly as a differentiable function of x. So y has not been solved for explicitly. So let's talk a little bit about notation. So we have used primarily y prime, but we've also used dy dx. So let's talk a little bit about this. What this means is the derivative of y with respect to x. And we read this dy dx. So the numerator tells you what you're deriving, and the denominator tells you what you are respecting. Now they give us some guidelines for implicit differentiation. So first we want to differentiate both sides with respect to x. We want to make sure that we do isolate dy dx. So just like we've used to solve for y in an equation, now we're going to solve for dy dx. We'll factor this out and then finally solve for it.